So we're going to do two questions that are very similar. First one is asking, consider the surface cylinder x squared plus y squared equal to 9. Find the inward unit normal vector to the surface of the cylinder at an arbitrary point x, y, z on the cylinder, and express this vector in terms of x, y. And then the second part is asking to replace all the x, y, z in n with their cylindrical conversion formula. One thing that I want to mention, it makes sense that we can actually define an inward unit normal vector to the surface everywhere. And just something that we talk about later in the semester, but at this point you can see that visually, or that this is something inquiry-based, basically. Now, the next thing that I want to say is this is an implicit surface, and I can find a function of f of x and y and z such that this implicit surface is a level surface for that. And that's the function. It doesn't have z because z is a free variable. And so x squared plus y squared equal to 9 is a level surface. Okay. Now, the next thing that I want to say is that, so let's find a gradient. Let's make a unit, find the direction of the gradient by making it a unit vector, and then compare the direction in here, see if we can multiply by negative, or we should be keeping it the same as it is. So first thing I do is finding the gradient, and that's partial respect to x, which is 2x, partial respect to y, which is 2y, and then there's no z, so 0. This gradient is defined at any point x and y and z, right? So I don't have to plug in a point exactly in there. Now, I need to do the magnitude of the gradient. And that is going to be the square root of the first component to power 2 plus the second component to power 2 plus the third component to power 2, which is 0. Here is going to be 4x squared plus 4y squared, square root of that, 4 factors out, and out of the square root, it becomes 2. Now that we are at this point, remember, where was x and y and z? It was on the level surface, x squared plus y squared equal to 9. Therefore, x squared plus y squared is equal to 9 on at this point, and therefore I can take it out of the square root, and it would be 3, then times 2 is 6. Now, on the next thing that I want to do is to find a unit vector normal to the surface at point x, y, z. A unit vector would look like this. It would be 2x divided by 6, 2y divided by 6, and 0, which simplifies to x over 3, y over 3, and 0. This is 3. There we go. Now, to figure out if this point is pointing inward or outward, I should take a test point. Let's take a test point. A test point, it looks like this is a good test point. I don't know what exactly z is, but I can guess it's about 2. I can tell that it's sort of halfway between x and y, and meaning that there's a 45 degrees in there, and so I can write it as 3 square root of 2 over 2 and 3 square root of 2 over 2, and let's say z is 2. If I plug those in, I get x, it would look like this, right? It would look like 3 divided by 3, so square root of 2 over 2, square root of 2 over 2, and 0. And that's a vector pointing outward, right? That's the direction of that vector. Therefore, this direction is not the direction that I want, so I have to multiply by a negative sign. So I use the test point. Let me write it down. Test point. And the vector associated with that. And so the test point and vector taught me that I have to multiply by a negative sign. So n is going to be negative x over 3, negative y over 3, and 0. Okay. Now this is part A. Let's do the part B. In part B, I'm supposed to plug in the cylindrical coordinates. So n of r and theta and z would look like negative r cosine theta divided by 3, negative r sine theta divided by 3, and 0. Now, again, as I said over here, you cannot leave x squared plus y squared as it is because x squared, x and y and z are on this level surface. Over here, I can leave r as it is. R has to be replaced by 3. Otherwise, the problem is wrong. Because on this level surface, we have that r is always 3. X squared plus y squared is equal to 9. R is equal to 3. Now, after simplification, what I get is minus cosine theta and minus sine theta and 0. And that's my unit normal in that direction. Again, later in the semester, arriving at either of these unit normals should be a process that you can do in 1 minute. Practicing right now pays off at the end of this semester when we are at chapter 16 and 17. Chapters 16 and 17. Now, this was a question that we completely did. Let's do another question similar to that. In this question, it's asking, consider the surface of the cone, z squared equal to x squared plus y squared, and find the outward unit vector. It's n to the surface of the cone at any arbitrary point except for the origin. Why not origin? Because origin is where the gradient is going to be 0 vector and it's not going to be defined basically. Express the vector in terms of x and y and z. Then the next part is asking to replace x, y, and z by their spherical conversions. So again, as before, I want to find a normal vector, and the normal vectors come with the gradient. So I'm going to compute the basically a function that the surface is going to be a level surface for. So to do that, I take all the variables in one side, and I write z squared minus x squared minus y squared. Then z squared minus x squared minus y squared equal to 0, which is that cone is a level surface. Now the next thing that I do is to find the gradient. So gradient of f at x and y and z is going to be minus 2x minus 2y and 2z. And then I want to find the magnitude of gradient, which is square root of minus 2x to the power 2 minus 2y to the power 2 plus 2z to the power 2. And taking this, it's going to give me basically 4x squared plus 4y squared plus 4z squared. And there I get, 4 comes out, it's 2 square root of x squared plus y squared plus z squared. Now, here we talk about the cone. If this was a sphere, I had to replace x squared plus y squared plus z squared with a constant. Because this is a cone, I could manipulate a little bit, put it in another format, but this format is good enough at this point. The other thing that I want to mention is that this is not simplifiable. You cannot distribute that square root over the terms. This is all you can do at this point for the cone. For a sphere, you can take another step and plug in a constant instead. So that's that. Now let's find a unit vector. And the A unit vector would look like minus 2x over 2x squared plus y squared plus z squared, and then minus 2y over 2x squared plus y squared plus z squared, and 2z over 2 square root of x squared plus y squared plus z squared. Simplify this to the most you can simplify, x squared plus y squared plus z squared, minus y over x squared plus y squared plus z squared, and z over x squared plus y squared plus z squared. So again, you can kind of see, last time I gave you an exact test point, right? Here I give you an approximate information about the test point. I look at this and the outward direction is that way. Over here, the point looks like whatever x and y and z is in the point. All of them are positive in this case. And then n looks like that the x component and y component of n is positive, but the z component is obviously going downward. Therefore, coming back in here, if I had x and y and z positive, this would be the x component of this n is negative, y component is negative, z component is positive. So I have to multiply by a negative sign. So the actual unit normal that I want is going to be negative of that. So this was part A, and for part B, I have to replace all the x and y and z with the spherical coordinates. So I get n rho phi and theta to be equal to x is rho cosine theta sine phi. You have to always remember this. This is the distance formula. It's just equal to rho in the denominator. And then y is rho sine theta sine phi over rho. And the last one is minus rho cosine phi over rho. So rho and rho simplify and you get cosine theta sine phi, sine theta, sine phi, and negative cosine phi. So at this point, I noticed that, or I remember that the cone's upper nap of a cone and the lower nap of a cone, each one of them should be phi equal to a constant. And so let's say for the upper nap of a cone and lower nap of a cone, find that constant. And sorry, lower. Going back to the equation, I have z squared equal to x squared plus y squared. I know that tan of phi to power 2 is equal to x squared plus y squared over z squared. So tan of phi, according to that equation, this is going to be equal to 1. Tan squared of phi is equal to 1. Tan of phi equal to plus minus 1. So phi is either pi fourth for the upper nap, and p is equal to 3 pi fourth for the lower nap. Remember, you cannot put in negative pi fourth, and you have to put in 3 pi fourth. So going back in here, I see that for the upper nap, I have n of rho, and instead of phi, I have pi fourth and theta. For lower nap, I have n of rho, 3 pi fourth, and theta. And so that gives me square root of 2 over 2 times cosine theta, square root of 2 over 2 times sine theta, and negative square root of 2 over 2. And in this one, it gives me square root of, for sine of 3 pi fourth, still positive. It's in the second quadrant. And square root of 2 over 2. So for upper nap and lower nap, you get slightly different unit vector. And so that's that. Now let's see. How do we simplify these things? So when you're at this point and you noticed that basically you are ending up at add a phi equal to constant or rho equal to constant or theta equal to constant, replace them back. But when you cannot, over here, for example, when you had square root of x squared plus y squared plus z squared, you could not simplify that. The square root does not distribute over there, and it's not equal to constant for the cone, basically. It's equal to rho, but it's not a constant for the cone. So that sort of things you don't simplify. And similarly over here, when you had x squared plus y squared, that does not simplify any further, and then the square root doesn't distribute.